Here we have a cylinder vase with a height of 9.5 centimeters. We begin to put 1/4 cup of sand at a time. Our first measurement will come out to 0.5 of a centimeter. Going on the second measurement, we are adding another 1/4 cup of sand. We make sure to even out the sand in order to get an accurate measurement. The second measurement will be an even 1 centimeter. Going on our third measurement, we are adding another 1/4 cup of sand, and we begin to even it out. It is measured to be 1.5 centimeters. We continue with our fourth measurement, and it will be another 1/4 cup of sand. Evening out the sand. As you can see, the sand is a little bit unleveled, so we're having difficulty reading the measurement. So we begin to even it out a little bit more to get a more accurate result. And it will now come out to 2 centimeters. We continue with our fifth measurement, evening out the sand. We will now have 2.5 centimeters. Going on our sixth measurement, this will now be an even 3 centimeters. We even out the sand just to make sure. We remeasure it, and once more 3 centimeters. Going on our seventh measurement, we've added another 1/4 cup of sand. We've evened it out. And this measurement will be 3.4 centimeters. We are now on our eighth measurement, evening out the sand. This measurement will now be 4 centimeters. Finally, on our ninth measurement, we will find it to be 4.5 centimeters. Through this collected data, it is shown that it increases at a constant rate of 1/4 cup every 0.5 centimeters of height. Here we have a conical flask. We begin with our first measurement of 1/2 cup of sand. We use a funnel to allow the sand to go through the funnel without making a mess. As you can see, this flask does not have a normal surface as the other containers that we have used, so it is a little bit more difficult to access a precise measurement. In the end, we conclude with 0.5 centimeters. We now begin with our second measurement of 1/2 cup of sand. We even out the sand. And we get a total measurement of 1 centimeter. We're heading to our third measurement. We even out the sand in order to have accuracy. This measurement will come out to 1.5 centimeters. Between the first, second, and third measurements, there is a constant rate. We're now heading to our fourth measurement. We begin to measure. And there has been a spike. The fourth measurement is now 3 centimeters. We begin with our fifth measurement. We fix our funnel in order for all the sand to go through, in order to prevent errors. Begin to measure, and this comes out to 3.5 centimeters. We're now on our sixth measurement. We even out our sand. This will come out to 4 centimeters. Between the fourth, fifth, and sixth measurements, there is a constant rate. Heading now to our seventh measurement. It will come out to 5.5 centimeters. There has been a spike between the sixth and seventh measurement. We are now heading on our eighth measurement, quickly evening out the sand. resulting in a reading of 6 centimeters. We are on our 9th measurement, which will result in 6.5 centimeters. Through collected data, it is shown that every 3 volumes, there is an increase at a rate of 1/2 cup every 0.5 centimeters of height. Since the cross-section of the flask is not constant, it is not a linear graph. As the velocity increases, the height also increases, which will result in the flask filling slowly, then quickly.
Okay, so this is the taller cylinder. It measures 17.5 centimeters in height, and we're using the 1/4 of a cup measuring cup for the 1 volume. Okay, so here's our first cup, and with the first volume, it measures 1.1 centimeters. Here's the second cup, and it measures 2.2 centimeters. Third volume measures 3.3 centimeters. Fourth volume measures 4.4 centimeters. Fifth, and it measures 5.5 centimeters. The sixth volume and it measures 6.6 centimeters. The seventh volume measures 7.7 centimeters, right? My eighth volume measures 8.8 centimeters. And my last volume, volume number 9, this one measures 9.9 centimeters. So every volume, every increase in volume was also an increase in the height that the volume was taking up, and it was constant. It kept increasing by 1.1. Started with 1.1, 2.2, 3.3, 4.4, and so on and so forth. It increases at a steady rate of 1/4 of a cup every 1.1 centimeters. This is the vase, and it measures 19 total centimeters in height. The first volume is 1 centimeter. The second volume is about 3 centimeters. The third volume is about 4.5 centimeters. The fourth volume is about 6.5 centimeters. The vase is wider on the bottom, and then as it increases in height, it gets narrower and then is wider on the top once again. Because of this, the graph will start off with a slowly increasing height, then the height will increase much more per every volume put in, and then the height will increase at a slower rate. The fifth volume is about 8 centimeters. The sixth volume is about 10.4 centimeters. The seventh volume is about 12 centimeters. The eighth volume is about 13.6 centimeters. And the ninth volume is about 15.4 centimeters. Okay, so I'm going to be doing the matching. So the plugged funnel is graph B because you can tell how it increases very sharply, really quickly, because it's narrow at the bottom, and as soon as the sand hits the inclined funnel type shape of the vase of the funnel, the height increases at a much slower rate, and you can see that in graph B. Okay, so I'm looking for the ink bottle, and it's graph F because the ink bottle is constant, and you can see that in graph F it's constant, and then as it hits that kind of upside down funnel shape, it increases up, and it increases kind of sharply because you have that funnel shape and then you have another constant, but that constant is much narrower, so it is being filled a lot faster. So yeah, so now I'm looking for the vase, and that one is letter E because the vase is very wide at the bottom and very wide at the top and narrow in the middle. So the graph is going to slowly increase at the bottom. In the middle, it's going to take like a sharp increase, and towards the top is going to slow down again because of those white tops and bottoms. And now I'm looking for the bucket, and the bucket's graph should be increasing, and it's narrow at the bottom and wider at the top, so it should increase at a constant rate, but it's gonna be very quick, and then it's gonna change to a little bit slower because of the fact that the top is a lot wider. So the graph for the bucket would be A. Now I'm looking for the evaporating flask, and this one is sort of more narrow on the bottom, wider in the middle, and then more narrow on top. At the very top of the graph, since there is like a very narrow cylindrical shape at the tip, there should be a sharp turn up. So the graph is I. And the last one is the conical flask, which is much wider at the bottom, and then it gets narrow on top, but it's a very constant kind of from wide to narrow, and that's all it does. At the bottom of the graph, it should be very, very slow because it's so wide. So it'll take more volume to increase the height, but towards the more right side of the graph, the height should increase a lot faster. So the graph is D for the conical flask. So for graph C, it looks like the height increases at a very quick rate, very sharply with a smaller amount of volume, and that it increases at a slower rate because the container gets wider on the top. So I think a container that would be appropriate for graph C would be kind of like a T, like the letter T. Okay, and for graph G, the height increases at a very slow rate, as you can see. So the bottom must be wider, and then the height increases at a much quicker rate. Thus the top of the container must be much narrower. So maybe that could be an upside down T where the bottom is wider than the top. And then for graph H, the bottom increases, but then it gets narrower because the height is increasing at a faster rate, and then wider and then narrower. So this one's a little difficult, but I think it might look like one of like a flower pot, kind of like what is shown here in the picture.